Assalamualaikum and very good day I bid to my supervisor Dr. Jelani, Dr. William Pau and Dr. Mohtar. My name is Muhammad Haqimi and I'll be presenting my viva, the title Parametric Study of Double Axis Tracking Heliostats to Optimize Heliostat Field Efficiency. Before I start, let me explain about my problem statement. So basically, heliostat field efficiency is related to the distance of heliostat from the receiver. You can see that from this, three heliostats will be reflecting the sun radiation onto the receiver. Throughout this process, there will be like certain losses that will affect the heliostat field efficiency. Notice that when the distance increases, atmospheric attenuation and cosine loss will also increase. Therefore, it is imperative for us to find the optimum distance of heliostats, resulting in the best overall field efficiency. So I'll proceed my objective. So the first one is that to develop a mathematical model in MATLAB to calculate the heliostat field efficiency. Next is to determine the optimum distance of heliostats between 3, 6 meter, 9 meter and 12 meter and the facing angle relative to the center of the receiver. Then I proceed with methodology. I have chosen for the arrangement of the heliostats will be in a radial staggered pattern, and the heliostats are placed at the north side of the tower, and the angle will be the relative to the north of the tower, which is this is the line of the north of the tower, will be at 0, 15, 30 and 45 degree relative to the north of the receiver. Next I'll proceed with the process flowchart. So basically this is the flow for my simulation in the MATLAB. But first I'll be setting the parameters, and then setting the parameters, for example like heliostat height, distance, tower height, to get the to calculate the declination angle. Once I've done that, I can calculate the target angle and facing angle to get the angle of incidence. I can calculate the cosine efficiency, atmospheric attenuation, and I can use that to calculate the field efficiency. And then if the efficiency is not optimized, I can repeat the process by adjusting the distance at the setting parameters, and I can get the parameters. I can get the values for 6 meter, 9 meter and 12 meter of heliostat distance. That's what proceed with the result I obtained from MATLAB simulation. For 1 day simulation, which is the cosine efficiency, you can see that the cosine efficiency is in parabolic shape for 3 different distances: 6 meter, 9 meter and 12 meter. And the highest cosine efficiency can be observed at 6 meter at the afternoon, which is 12 p.m. that yields a value of 82.3%. 9 meter gives a value of 77.3 and 12 meter 74.1%. Next I'll proceed with the cosine efficiency at 6 meter for west side and east side. So basically we can see that from this figure, the cosine efficiency is higher in morning. This is because the surface normal pointing towards the receiver and sun is exactly opposite of it. So that's why the cosine efficiency is higher in the morning and lower in the evening at the west side. So we can see that actually the west side and the east side is symmetrical. So because we know that the sun rises from east and sets on the west, and we can see that the highest efficiency is recorded at angle of 45 degree, which is 90%. Let's proceed with the cosine efficiency at 9 meter. For this one, you can see that the cosine efficiency slightly decreased from 90% to 87% at 6 meter to 9 meter at afternoon. You can also notice that the other angles, which is the 15, 30 and 0 degree, also slightly decreasing compared to the 6 meter previously by value of 1 to 2% less. Let's proceed with the 12 meter distance of heliostats. Okay, so basically the efficiency decreases from 90% at the 6 meter to 84% with this 12 meter at the afternoon. You can also notice that other angles also shows a very big decrease in value compared to 6 meter by 3 to 4%. Let's proceed with the atmospheric attenuation. So basically this is the reduction in intensity of solar reflection as the distance increases. You can see that from the figure, the atmospheric attenuation efficiency at 6 meter is 99.25%, 9 meter 99.22% and 12 meter 99.18%. So basically what we can say about this is that the further placement of heliostats, the higher the atmospheric attenuation loss. However, this atmospheric attenuation, the value is constant every day because it's only a function of distance. Let's proceed with this. I've also done a 1 week simulation for this heliostat field efficiency. So this overall efficiency include the cosine, atmospheric attenuation, and mirror reflectivity. So basically, mirror reflectivity efficiency is established as 88%. And another thing is that shading and blocking is not focused as main loss in efficiency, as the cosine loss is the biggest factor in lower of field efficiency. Okay, so basically from the simulation we get the highest heliostat field of efficiency can be observed at 45 degree at a distance of 6 meter. At 6 meter 45 degree, that yields a value of 88.7%. Next, as a conclusion, I believe that is the further the heliostat from the receiver, the bigger cosine and atmospheric attenuation loss. So basically, to answer back the objective, the optimized heliostat field for the given parameters that I have chosen can be observed at 6 meter away from the receiver and 45 degree relative to the center of receiver, which give a value of overall field efficiency at 88.7%. So as a recommendation, I believe that to better my project, I can increase the simulation time from 1 week to 1 year. This is to increase my credibility of the project. Next, I believe that it's better to carry out the simulation and experimental together to increase my credibility also for the project. Last but not least, as a recommendation, it's better to include shading and blocking into field efficiency, because the heliostat field efficiency comprises of all the losses. With that, I end my presentation. Thank you very much.